In this video, we're going to focus on chemical hydrogels. So chemical hydrogels are those that are cross-linked through covalent bonds. These can be created in a number of different ways, mainly number one, by copolymerization of monomers or macromers with difunctional linkers, as we can see here. For example, here we could have a monomer that has a vinyl group, something like a acrylate or methacrylate group that can be polymerized through free radical polymerization together with a cross-linker that has two such vinyl groups. And then when these are copolymerized, of course, you're going to get a cross-linked chemical network because of the cross-linker being able to link two independent polymer chains. I want to point out right here that whenever I say a macromer, what I'm talking about is a polymer that already has been polymerized, but that contains a group that can be further polymerized. Thereby, that group enables us to make this a part of a new polymer chain that would grow along this carbon-carbon bond. So this is an example of a macromer. That's polyethylene glycol methyl ether methacrylate. And of course, you would be polymerizing this vinyl group, the carbon-carbon double bond, into a new polymer chain that would have now this prepolymer as a pendant group. And here when I say difunctional monomers that you would utilize like a cross-linker, an example of that would be something like polyethylene glycol dimethacrylate that again has two of those vinyl groups that can be polymerized. Here also we can see that we could cross-linked polymers, We can similarly take just macromers and polymerize them together if the macromers contain two or more of these polymerizable groups, then you would end up also with a hydrogel network. Number two would be to cross-link polymers by utilizing radiation. That radiation could be ionizing radiation such as electron beam, gamma rays, or X-rays, which would excite the polymer and produce a cross-linked polymer network through a radical reaction. With all of these methods, you would end up with a cross-linked polymer system. Number three would be to chemically cross-link water-soluble polymers with a difunctional linker, as is shown here, number three. So for example, we have a hydrophilic or water-soluble polymer that has two groups that can be reacted, and if we react that polymer with a linker that is multifunctional, in this case it would have to be trifunctional or higher order functionality that would enable these polymer chains that are linear to be able to be cross-linked. Similarly, we could have a multifunctional polymer that has a multitude of reacted pendant groups and reacted together with a number of different linkers to end up with a hydrogel network system. An example of these multifunctional linkers that could be utilized in these kind of processes are shown here. You could have a 4-arm polyethylene glycol, such as the one shown here, with a number of different and functional groups. The particular one that I'm showing here is an N-hydroxysuccinamide group that is reactive toward primary amines. But you could easily purchase a polyethylene glycol that is multi-arm. They sell 4-arm and 8-arm polyethylene glycol that has amine groups, carboxylic acid groups, diol groups, alkynes, acids, all kinds of functional groups, depending on what chemistry it is that you're trying to do. Similarly, you could have a difunctional linker, such as a PEG carboxylate that has two carboxylic acids that could be utilized to cross-link another polymer system. One thing that I want to point out is that these chemical hydrogels have irreversible association, because what we're doing is that we're forming covalent bonds. So those covalent bonds would need to be broken through other chemical reactions in order for the hydrogel to degrade. First example of a chemical hydrogel. This is an example that I had shown you before. It's actually from my postdoctoral work, and this is basically the preparation of a hydrogel that utilizes itaconic acid, which is basically a small monomer that has the vinyl group that we need to polymerize, but it also has two carboxylic acids that enable us to make a hydrogel that is pH responsive. That monomer was cross-linked or was reacted together with a macromer. This macromer is polyethylene glycol methyl methacrylate. Notice here the vinyl group to enable us to polymerize it, but yet it was already a polymer that had polyethylene glycol, where the PEG now will become a pendant chain in the hydrogel. And then that whole system was cross-linked by utilizing tetraethylene glycol dimethacrylate, which is basically a short PEG oligomer with 4 repeat units that have two of those vinyl groups that would enable this to act as a cross-linker between two chains. And here I'm just showing like a snapshot of what the polymer would look like once we actually carry out the polymerization. In this particular case, this was a UV-initiated free radical polymerization utilizing a UV initiator. And the chemical structure is shown. As you can see, we have itaconic acid in several places, like this one, this one, this one. Those are itaconic acid. I'm going to try to highlight with a different color. The PEG macromer, which is the polyethylene glycol methyl methacrylate, that would basically have become pendant groups that are coming out of the chain. And then finally we have the cross-linker, which I'm going to try to put in a blue color. And that's the tetraethylene glycol dimethacrylate that is basically bridging independent chains together, forming now the cross-linked polymer system. Whenever you do this kind of chemical hydrogel polymerization, of course, you need to use a monomer. Those monomers could be acrylates or methacrylates. They could be monofunctional or they could be macromers, as is shown in this case. You also need a difunctional or multifunctional cross-linker, such as the tetraethylene glycol dimethacrylate shown here. You will need an initiator. That initiator could be a thermal initiator, a UV initiator, or you could utilize redox initiation. And finally, you have to carry out the polymerization, which in this particular case would be free radical polymerization. All right, oops, sorry about that. Another example of the preparation of a chemical hydrogel is shown here. This is polyvinyl alcohol, which is being cross-linked, with glutaraldehyde. So notice that we are already starting with a polymer, and what we're doing is trying to link individual polymer chains utilizing a cross-linker that is, in this particular case, difunctional, glutaraldehyde. This glutaraldehyde would basically cross-link independent polyvinyl alcohol chains by forming this acetal bridge that is shown here. Another type of cross-linker that you could utilize would be basically any kind of dialdehyde molecule. And glyoxal, which is shown down here, is the smallest dialdehyde that can be utilized. On the bottom, I also have another cross-linker that you could utilize, which would be a borate ion. This borate ion would have the ability to bind two polymer chains, as well as is shown in this particular case, also with polyvinyl alcohol. All right. Another set of chemistries that have been more recently utilized to create hydrogels are called these orthogonal chemistries. Orthogonal chemistries are basically any kind of chemistry that can be carried out in the presence of biological molecules or even live cells, and that have no side reactions with those biological molecules. So they can occur in the presence of those molecules, but they would actually not react with any kind of biological molecule. They don't react with proteins, they don't react with oligonucleotides or polysaccharides, basically. And they can also occur under very mild conditions. So in fact, you would be able to carry out this reaction in the presence of cells, or even by injecting into an organism, an animal or a human. These reactions tend to be rapid, and most of them don't need initiators, and so they're basically biocompatible reactions or biocompatible chemistries that are orthogonal in that they occur, but they don't interact with what's already there. There are several types of orthogonal chemistries. One of the most widely known or most widely utilized in biomedicine is click chemistry. These click chemistries, there's a number of different ones, but you actually heard about click chemistries from the seminar by Amber Lucas. She also mentioned that there are several click chemistries. I'm just going to talk about two in this particular presentation. So the first one is acide alkyne chemistries. So acide would be this functional group right here. This is an acide. And then an alkyne would be a carbon-carbon triple bond. When these two functional groups react, they end up forming a triazole bond, as is shown here on the right-hand side. Now that acide alkyne reaction needs to be catalyzed. This reaction is catalyzed, in fact, by copper 1. So you need a copper 1 catalyst to enable that reaction to occur. Here on the second row, what I have is actually a similar type of acide alkyne reaction, but where now the alkyne is part of this cyclic molecule. And notice that we're using a cyclooctane. This kind of reaction is strain promoted, and because of that, it doesn't require the use of a copper catalyst. So these are labeled copper-free click chemistry reactions. Again, they're mediated by the strain of this octane ring or cyclooctane ring, and there's a number of different molecules that include that cyclooctane that have been utilized. And as you can see here at the bottom, there's a number of different cyclooctanes that have been synthesized to enable this reaction to occur. Commercially, you can purchase a number of different polymers that have already been functionalized with this dibenzocyclooctane that can react directly with the acide group. This N3 is the same thing as this acide group right here, N3. And it was this to react as well in order to form the same kind of triazole bond that would link two polymer chains together. In this particular case, I'm showing the reaction of a di with a carrier, but imagine that this would be one polymer chain versus another polymer chain that we're trying to cross-link. All right, so that's acide alkyne chemistries. Another type of click chemistry is this diol-ine chemistry, and that's shown here at the bottom. So what we have is a diol molecule, meaning a molecule that has this sulfhydryl group. That diol molecule can react with an ine, which means a triple bond between two carbons, similar to it's basically an alkyne, that's what it is. And we react that alkyne and that diol molecule in order to form an alkenyl sulfide system. That reaction can be carried out in the presence of UV light or utilizing a radical initiator. And it's just another method that has been utilized lately to be able to form or cross-link hydrogels. All right, on the next slide, I have the second type of orthogonal chemistries, and those are Michael addition chemistries. In this particular case, I'm showing the diol-ine reaction. Again, diol means that we have this sulfhydryl group decorated onto a polymer chain. And then we are reacting it in this particular case with an ene molecule, meaning a carbon-carbon double bond, an alkene. And the reaction again is Michael addition, and it would result in the formation of an alkyl sulfide bond between the two chains. Um, the group of Dr. Christopher Bowman at the University of Colorado has utilized this reaction for the formation of a number of hydrogel systems. And this particular reaction occurs in high yield, has good stereoselectivity and high rate. And it can occur through two mechanisms. One of them is a free radical addition that is initiated either with light or with heat or with radical initiators, or it can be catalyzed through the use of base or a nucleophile. This is one particular example where they have used the thiol in chemistry. So thiol, again, the sulfhydryl, are reacting with an alkene, carbon-carbon double bond, to form a hydrogel. So what they did is that they utilized this four-arm polyethylene glycol system that has these vinyl sulfone groups. The vinyl provides the alkene that we need to carry out the reaction, right? And so what they did then is that they reacted this with a cross-linker, which is a vis diol, so it's a molecule that contains two thiol groups. This would act as the cross-linker, bringing together many of these together. In this particular case, this is actually an enzyme-sensitive peptide. That's what ESP stands for, meaning that this cross-linker would actually be biodegradable through the action of enzymes that are liberated by the cells that they were trying to utilize this hydrogel for. And at the same time, since you remember that polyethylene glycol is very hydrophilic and is not conducive to cell adhesion. So what they did was to also utilize a thiol functionalized cell adhesion peptide in order to modify the hydrogel, or to provide anchoring points on the hydrogel for cells to be able to attach. That cell adhesion peptide, as expected, is basically a peptide of RGD, which we had mentioned before as being a good peptide for cell adhesion. Another example here is a copper catalyzed click chemistry, meaning the reaction of acids with alkynes in the presence of copper. As you can see here, they had cell adhesion cell adhesion peptide, which is the red sphere, that is functionalized with this diacide molecule, and which would be able to react with the alkyne groups of this four-arm polyethylene glycol, forming triazole bonds in between. And this was reacted with copper sulfate, which is copper 2, and then with sodium ascorbate. So sodium ascorbate has the role of reducing the copper 2 plus, which is what we're beginning with. Oops, what happened here? It's not, I see. This is copper 2 plus, and in the presence of sodium ascorbate, it is reduced to copper 1 plus, which is what we need in order to catalyze that reaction to be able to form the triazole bonds. And so by utilizing this kind of simpler system, they were able to create a cross-link hydrogel system that included not just polyethylene glycol to make it hydrophilic, but also cell adhesion peptides to enable the integration of cells into this system. Another example of the use of click chemistry, in this particular case, copper-free click chemistry, is a system where we're utilizing that cyclooctane. So to do this, what they ended up doing was to utilize a polyethylene glycol, from which they did the ring opening polymerization of this monomer. Notice that this monomer contains two acide groups. So upon ring opening, basically what they end up with is a polymer on both sides of the polyethylene glycol that contains the acide groups. Now, one thing to notice is that this polymer is actually a polycarbonate that contains this carbonate group right here, and right here, which is actually degradable as well. So by doing this, they were creating a tri-block copolymer system that was hydrophilic in the center to enable the formation of a hydrogel, but that also contained biodegradable linkages and the A side groups to enable click chemistry to occur. This part was done synthetically, not in the presence of cells. But I would say also separately, what they did is that they took different polyethylene glycol linkers, either a linear polyethylene glycol of 6,000 or 20,000 molecular weight, or a 4-arm polyethylene glycol of 10,000 molecular weight, and they functionalized those linkers with this molecule. Notice that this molecule has the dibenzocyclooctane molecule that we need in order to be able to carry out click chemistry. In this particular case, they utilized the carboxylic acids to be able to react with the hydroxyl groups at the 2 ends or 4 ends of the polyethylene glycols in order to give them the DBCO or dibenzocyclooctane functionalized PEGs. That's what is shown here, where the R groups are basically this dibenzocyclooctane moiety. So once we have the functionalized polyethylene glycol here, which is functionalized with the alkyne molecule that we need. And then here we already have the tri-block copolymers that have the A side groups. Then they could actually put those together in the presence of cells under physiological conditions and enable the gel to actually form. In this particular case, they were using bone marrow stromal cells, and they showed that they were able to encapsulate them utilizing very mild conditions and leading to to significant cytocompatibility, meaning that the cells were actually able to be entrapped and were viable. They were not killed, basically. So this is a really cool work showing a way to create hydrogels that could be utilized for tissue engineering purposes, for example. All right, so to summarize some of the ways that can be utilized to create chemical hydrogels, one of them is to cross-link polymers in the solid state or in solution, utilizing either radiation, for example, irradiating polyethylene oxide, which remember is the same thing as polyethylene glycol chemically, in water. Similarly, we could utilize chemical cross-linking, for example, the treatment of collagen with glutaraldehyde or bisepoxide. And I've actually pasted the chemical reaction that is mentioned here. So here we have glutaraldehyde. In this particular case, this is gelatin instead of collagen, but the reaction would be the same, where from the protein from the protein in this case or peptide, we're utilizing the primary amine groups that are going to be cross-linked with glutaraldehyde, forming this kind of bridge in between the two chains. The second one was the use of bisepoxide, and you can see that, where did I put it? Wait, oh, I swear I had put it here. So we can utilize, this is a bisepoxide, this is one epoxide, the other epoxide group, and assume that this is a polymer system that has hydroxyl groups. We can basically use the bisepoxide to bridge together the two polymer chains, if you would. All right. Similarly, we could utilize multifunctional reactive compounds such as polyethylene glycol, which is a molecule that has 2 hydroxyl groups together with diisocyanate to form a polyurethane, and I have that somewhere here. This is a diol molecule. Assume that it is polyethylene glycol, for example, and this reacts with a molecule that has 2 isocyanates in order to form a polyurethane system. All right. Oops. I actually forgot to mention, with the glutaraldehyde, you could actually do 2 different reactions. So if your polymer chains contain amine groups, then this is the reaction that occurs. But if your polymer chain contains hydroxyl groups, then this is the chemical reaction that occurs. In any case, the glutaraldehyde just has the role of linking the two polymer chains. That's all that I wanted to show you. All right, the third way to form a hydrogel, actually the second form in this particular case, is to copolymerize a monomer and a cross-linker in solution. For example, hydroxyethyl methacrylate and ethylene glycol dimethacrylate. Remember that when you do this kind of polymerization, you always need a monomer, but you also need a cross-linker that is at least difunctional, as in this case, the ethylene glycol dimethacrylate. And I've shown that reaction here on the right-hand side. This is hydroxyethyl methacrylate that has one vinyl group, and then we have ethylene glycol dimethacrylate that contains two methacrylate groups that would enable the polymerization to take place. Notice that from the heme, it is that carbon-carbon from here that ends up in the polymer backbone. And from the dimethacrylate, it is also this part that ends up here, carbon-carbon. The other side, it's still available to react. So this would actually end up reacting with other heme monomers, forming another chain on this side, right? And that creates the hydrogel. Number 3 here is to copolymerize a monomer and a multifunctional macromer. For example, bismethacrylate terminated PLA, PEO, PLA with a photosensitizer and light irradiation. Or number 4, polymerize a monomer within a different solid polymer to form our interpenetrating gel. And again, we'll talk about interpenetrating gels toward the end of this whole section. This next slide lists a number of different polymers that are utilized in the preparation of hydrogels. They are separated by natural polymers versus synthetic polymers. Among the natural polymers, we have anionic polymers such as alginic acid, which I have the structure of on the next slide, pectin, carrageenan, chondroitin sulfate, and dextran sulfate. We also have cationic polymers such as chitosan and polylysine. I have the structure of chitosan on the next slide. We have amphipathic polymers that are both cationic and anionic, which include collagen, gelatin, carboxymethylchitin, and fibrin. And then neutral polymers such as dextran, agarose, and pullulan. Remember that agarose is a polymer that we discussed in one of the previous student presentations. All right, in terms of synthetic polymers, a lot of them are things that you have already known. Notice that here we list some polyesters. Of course, notice that they're all listed as block copolymers, where we have the PLA polyester together with polyethylene glycol on both ends. Similarly, here we have polylacticoglycolic acid or PLGA in a tri-block copolymer with polyethylene glycol. Here's polycaprolactone, polyhydroxybutyrate, and then here we have a number of others that you might not have heard, such as, what was it? Oh my goodness, I went crazy. I went blank here. Propylene fumarate, and here is polybutylene oxide. Let's see, we also have a number of other polymers here, and some of the ones that you might recognize are polymers that contain polyacrylamide, polyanisopropyl acrylamide, which is the temperature responsive polymer. What else? Polyvinyl acetate, or polyvinyl alcohol. And I think that's about all the ones that you are familiar with. On the next slide, I have the chemical structure, so the most important ones. So polyethylene glycol, of course, which I expect that you know by now, polyvinyl alcohol. We have polymethyl methacrylate, methacrylic acid, and acrylic acid, and hydroxylethyl methacrylate, acrylamide, and N-isopropyl acrylamide. All of these are polymerized by free radical polymerization. These ones right here. We also have poly-N-vinyl pyrrolidone. And then the two natural polymers that I have in this list are chitosan, which is a cationic polymer, and then alginate, which alginate is the salt form of alginic acid, which I had listed on the previous page. Now, one of the things that I want to touch on this particular video is hydrogel microfabrication. So there's a number of different ways for us to get specific geometries out of these hydrogels at the micro scale. One of the ways is to do emulsification, where basically you would take the monomers perhaps and put them into a non-solvent. For example, if your monomers are not water soluble, you could disperse them into water and carry out the polymerization in the form of droplets. Or if they are water soluble, then you could do emulsification into an organic solvent in which they are not miscible, and then carry on the polymerization in those droplets in order to enable you to form individual droplets as shown. Another method is micromolding, where basically we have initially a pattern surface onto which we apply a pre-polymer, meaning a solution of your monomers or a solution of polymers that have not yet been cross-linked. We then utilize another solid surface to basically stamp on top or to mold the pre-polymer solution, such that the prepolymer is now only within the cavities formed between the two surfaces. We then allow the polymer to set, either polymerize or form the secondary interactions. And then once we open the mold, we would end up with the individual hydrogels at the microscopic scale. Another method that is used significantly is photolithography, which we had already talked about before, in which basically we apply a prepolymer solution. In this case is the monomers and cross-linkers and a UV initiator. We then apply a mask on top. That mask has the pattern that we want to obtain on it. And basically these open parts are the parts that are going to allow UV light, which is utilized to initiate the polymerization, to go through. The light goes through those openings, and it cross-links or polymerizes the hydrogel in the shape of the pattern that is on the mask. So in this particular case, we would get this kind of square-shaped hydrogels. Another method is scanning light lithography, in which we have a prepolymer solution that also includes a UV or a light initiator. We then apply the UV light in specific locations and basically write on the polymer solution, thereby forming a gel wherever that light is focused. In this particular case, you could write this kind of cylindrical or donut shape hydrogels, or really whatever shape you would like. And this is a really interesting method in which you could get significantly interesting geometries. Another method is to utilize microfluidic techniques. For example, here we have a non-solvent, or we have one stream that is just is just a solvent. And then on this stream, we bring the prepolymer solution. By utilizing microfluidics, we basically have no mixing between the two streams, and we are able to separate individual droplets of our prepolymer solution, which can then set either on their own or through UV radiation to polymerize the hydrogels in this sphere shape. And finally, we could have gel printing, where basically we are kind of applying the prepolymer solution as needed along a specific geometry that we want. Basically kind of like writing, but we're allowing the polymer to set as we write. Finally, the characterization of hydrogels. Basically, it depends on whether you have macroscopic or micro or nanoscaled hydrogels. For the case of macroscopic hydrogels, one of the main characterization techniques that are utilized is to do swelling studies. Those could be dynamic or equilibrium swelling studies. In a dynamic swelling study, you would actually investigate the swelling as a function of time, while in an equilibrium swelling, you would allow the hydrogel to reach equilibrium before you measure the extent of swelling. The swelling is typically measured by looking at the weight between the swollen gel versus the dry gel. In some cases, you might utilize the dimensions instead of the weight in order to look at volume changes. Another method is to utilize cryogenic electron microscopy to look at the porosity or at the porous structure of the hydrogel. The reason why cryogenic electron microscopy would be utilized is that in this particular case, you don't have to dehydrate the gel. You would take the swollen equilibrated gel and you would freeze it in liquid nitrogen and be able to observe it in this frozen state, such that we don't get the drying effects that would occur if we utilize normal electron microscopy, in which the sample has to be completely dehydrated and you might not be able to see the structure of that hydrogel. Mechanical properties is another thing that can be measured for microscopic hydrogels, and those include tensile testing as well as dynamic mechanical testing. And I refer you guys to this paper, which goes into detail into all of the theory and methods that are utilized for mechanical testing. But just kind of briefly, for tensile testing, the hydrogels would be typically cut into a dumbbell shape. That dumbbell shape enables you to be able to grasp the hydrogel from the top and the bottom without breaking it. Then the testing would actually be carried out ideally with the hydrogel immersed in a water bath. So you would require kind of the right system to enable you to do that, to be able to do tensile testing while the sample is immersed in water or in whatever buffer it is that your hydrogel is equilibrated in. We then would plot the stress versus strain, and the slope of the data, of the stress strain data, would provide you with the shear modulus, which in turn is proportional to the molecular weight between crosslinks. So that's an important parameter to characterize for these kind of hydrogels. Similarly, if you could utilize dynamic mechanical testing in order to look at the time-dependent viscoelastic properties of the hydrogels. In a typical testing system, you would apply a sinusoidal load in shear mode to the hydrogel and be able to measure at the same time changes in the elongation of the sample utilizing a strain transducer on the other side. Let's see. One thing that's important is that in any kind of tensile testing or mechanical testing, you do want to maintain the hydrogel in the swollen state, and so drying of the water during the testing can significantly affect the results. So for that reason, as I mentioned, for tensile testing, ideally you would have the sample immersed in water or in buffer while testing. And in this other particular system, since you cannot typically immerse it, what you can do is to try to seal the system utilizing silicone or petroleum grease in order to prevent water loss. Now, if you have a micro-scaled or nano-scaled hydrogel, obviously you won't be able to do swelling studies in the same way, or you won't be able to do mechanical testing in the same way, but there are other methods that can be utilized. One of the things that is typically done is particle sizing by dynamic light scattering, and that can be utilized for looking at the swelling of the hydrogels in the micro or nano scale as well. Again, you would be looking at changes in the diameter of those hydrogels. Cryogenic electron microscopy is still valid for these kind of systems. And then for mechanical testing, there's a number of different ways. One of the ways is to utilize atomic force microscopy, and there are other methods that could be also important.